So the genesis of this presentation was that I like using baluns. I've liked using baluns ever since I discovered that I built a J-pole and I could change the match of the J-pole by putting my hand on the coax. And I thought that's just not right. So I started using little baluns and chokes and things, and I had a lot of rules of thumb for them, but it was kind of like, well, they're magic. They work because they add goodness. It's like they add vitamins to your antenna. And since it's often easiest to learn something if you have to teach it and explain it to other people, I decided I would commit to giving a presentation on taking the mysteries out of baluns so that I would have to take the mysteries out of baluns for myself. So let me see here. So what's all this then? A balun is, according to Wikipedia, an electrical device that converts between a balanced signal and an unbalanced signal. It might change the voltage and the current, the impedance, but it doesn't have to. There is nothing that necessarily changes the voltage to current ratio that makes it a balun. As hams, we often are confused about whether we need a balun and what kind we need if we do. Worse, some of us, myself included, got kind of confused over the years about what we mean by balanced or unbalanced. What does that really mean with RF or pro audio for that matter? We generally start out as hams thinking the difference is pretty simple. Obviously, those things up on top are balanced lines, right? Because they're symmetrical. They have two wires, a left wire and a right wire, and they're both the same. And that thing on the bottom is clearly unbalanced because, well, the inside and the outside are different. They're not symmetrical. It must be unbalanced. So that gets into somewhat more complicated feed lines that are important to us so that we don't usually use them at RF. Two-wire power cord from my laptop. Is that balanced? Well, I mean, it looks symmetrical. Or Romex. I mean, look how symmetrical those wires are. They're exactly the same except for their color. That must be balanced feed line, right? Well, it turns out they're not. They're not at all, not even close. That's why we can get electrocuted by them so easily. So what's the difference? The reality is that you can't actually tell whether a line is balanced by its shape. It's all about the ground. Whether we call it an earth ground or a circuit common or the chassis or the frame of the generator, it's all about the relationship of the feed line and the antenna to the ground. A balanced transmission line has equal and opposite currents between its conductors. And I mean opposite in phase too, 180 degrees out of phase. And equal impedance to ground, or whatever you're using for ground, outer space, the ionosphere, the generator frame, from both of its conductors at any common point. If you're 10 inches along the feed line or in the middle of each antenna arm, they have to have equal impedance to ground. An unbalanced transmission line can and usually still will have equal and opposite currents between its conductors, and especially on the inside of a coax, they will be 180 degrees out of phase. And yet it's still unbalanced. So, I mean, let that sink in. Inside of a piece of coax, the currents must be equal and opposite and perfectly out of phase, or they'd be on the outside. But yet, coax is still normally unbalanced. What makes most coaxial cable unbalanced is the same thing that makes your house wiring unbalanced. Ground. It's not equal and opposite impedance. It's not equal, impedance to ground. That neutral wire is bounded to the big stick. With your coax, the shield is normally connected to the outside of your rig or your matching unit, and that is normally connected to the big ground stakes somewhere, or your radial network, or the ring of ground stakes around your house. That's what makes it unbalanced. The impedance to ground is not equal. One of those conductors has a really easy path to ground, and the other does not. So if your coax magically did not have one side connected to ground, it would be balanced. Nothing to do with the shape of the conductors. Balance is also confusing because people speak about antennas as imbalanced, and often what they really mean is symmetrical. Sometimes they do mean the same thing as with a feed line, equal and opposite currents out of phase with equal impedance to the environment in each corresponding part. So here's a little homebrew buddy pole. I loved building that. I have a lot of fun. I use it all the time. I'll probably be using it again this weekend. Great. It's, not perfectly balanced, but it's pretty close. It's about 15 feet up. The sides are the same size. There's nothing metal in either one. They're going to have equal and opposite currents, and they're going to have the same impedance to ground from, each tip or each middle or each point 1/4 of the way along. Small loops are usually pretty well balanced too if you keep metal objects away from them. Pretty much the whole thing has the same impedance to ground usually. Now, I had to draw this antenna in. I couldn't find a picture of someone dumb enough to put their inverted V next to their Quonset hut, so I imagined someone did. This would not be a balanced antenna. One of those sides of that antenna has a very low impedance to ground. There's that big metal capacitor right next to that arm of the dipole. So we would then have what we call an imbalance current, an antenna current, a common mode current flowing on the feed line, which we probably would anyway because it's coax. I'll go into that in a minute. Of course, other antennas aren't unbalanced because we goofed up. They're unbalanced on purpose. In a ground plane vertical, I really hope that your radials have a very low impedance to ground, much lower than the vertical element does. That's what they're there for. Whether you feed it with coax or even feed it with twin lead, I have fed a ground plane vertical with twin lead. It worked well. You still have that common mode current on your feed line. It's still unbalanced because they don't have the equal impedances to ground. An unequal impedance to ground at any part of your antenna system, be that the feed line or the connectors or the antenna elements, any part may cause the so-called common mode currents, I3, the antenna current. This is the part of the current in your transmission line that isn't equal and opposite in both conductors. It might be flowing on your twin lead. It might be flowing on the outside of your coax. Either way, it has the same effects, and we call it the same thing. It can be caused by your transmitted signal or also a received signal, and that can be especially annoying because it changes your antenna reception pattern. You can't null out the noisy guy you were trying not to hear. So why do we care? I kind of hinted at a reason. Is common mode current actually a problem? Is balance something we need? Does the balun make our antenna more powerful? So why in general do we need a balun, particularly with coax? I used to think when I first became a ham that there was something magic I didn't know about, that when you hooked up the two arms of your dipole to your coax, meant you have one arm hooked up to the center and one arm hooked up to the shield. And there was something magic that made the current on the shield go out your antenna and not back down the shield to the ground. I have since learned, this is on the extra class exam, that there is no magic. There is no such magic, at least with antennas. The current will go right down the outside of that shield if it wants to. If it has a very low impedance path to ground, perhaps you've got a really great ground and your coax is half a wavelength long, you will actually get a lot more current running down the outside of that shield than you will in the arm of your dipole. Oopsie. It's the two sides of the antenna also don't have an equal path to ground. It's kind of as if there's this extra sneak circuit, with an impedance, between that right-hand arm of the dipole and the output of your transmitter. It's an extra circuit that you may not want. So an antenna does not actually need to be balanced to work well. A balanced antenna does not make your coax balanced. Some antennas, like the off-center fed dipole, are deliberately asymmetrical and imbalanced, and they're still fun. So balancing your feed line and eliminating that antenna current might reduce RFI to appliances in your house. It might reduce received signal interference. It might eliminate RF in the shack. What it will do is make your voltage standing wave ratio and your antenna pattern much more predictable. You will not get that effect if everything is isolated from ground, where you add an extra few feet of coax and your antenna pattern changes or your impedance changes, or you put your hand on the coax and suddenly your VSWR is 5-to-1. A balanced feed line will not lower your cholesterol, and it will not make your antenna more efficient or your station more powerful. All that power you were pumping into the feed line is going to go somewhere. We're not making more power by adding a balun. I used I3 here because this slide, it's poor design. This slide has too many words on it, so I had to say I3 for antenna current or common mode current. You need a balun if you need a reliable pattern. This happens to me a lot because there will be someone who starts calling CQ right on top of the person in Slovenia, and they will be much closer. They're probably going to be in Florida, someplace right kind of in the first hop on that band, and they're going to be really loud. I want to point the end of the dipole at them and make them go away. You're troubled, as I was with my J-pole, with SWR changes when your feed line length changes. You're picking up interference from equipment near your feed line. Your microphone or rig gives you bites. I don't have a middle microphone. Your auto-tuner randomly retunes when a bird lands on your coax. I didn't get that from birds, but I did get it from squirrels. That was discouraging. And your transmissions trigger your smoke alarms or turn off your air conditioning in your shack. That happened to me too. Common mode current is not a problem if you don't care about your antenna pattern. Or in fact, you might intentionally, some off-center fed dipole designs do this, use that common mode current to fill in deep nulls in the antenna pattern. If you want to hear everybody in every direction, you don't want a sharp pattern with deep nulls, of course. If you don't happen to have problems with RF in the shack, you don't receive interference, if none of that stuff applies, or if it happens, and this is particularly true on 40 and below, if your feed line is very electrically short, you may not have much issue with common mode current flowing. You don't get a lot of impedance transformation in a short feed line where a high impedance one place becomes a low impedance that attracts current in another. So electrically short feed lines, often the balun doesn't change your antenna pattern or provide many benefits. So how does a balun work? I'm going to start here by talking about coax, because coax is kind of a big challenge. To get rid of that I3, the common mode current on the outside of the coax, it would be really great if we could just cut the shield. Trust me, that doesn't work. When it happens by accident, your coax stops working and you get weird, strange effects. So we have to do something that somehow just cuts the outside of the coax, but not the inside. It turns out there's a way to do it because of skin effect. A current that isn't equal and opposite will get pushed to the outside of the coax by skin effect, just like currents in the wires are pushed to the skin of the center conductor and the skin of the inside of the shield. Well, any current that isn't equal and opposite inside the coax ends up on the outside of the shield. It's kind of neat and convenient that way. So if we could just add impedance to the outside, we could cut the outside and not cut the inside. Of course, one way to do that is to break the electrical path with a one-to-one transformer. That's very commonly done in the audio world. You probably, if you did HF digital, you might have a device with one-to-one matching transformers like this. The problem is bandwidth. We have a lot of frequency, and it's hard to design a transformer that, a conventional transformer at least, that works well from 160 through 50 megahertz. Coax covers typically, let's say 1 megahertz to 900, or in some cases for satellite coax, say 50 to 1.2 gig. There are no transformers like that. Well, none that work well. So because most rigs have an unbalanced output and the inside of the outside of the coax shield are separate wires, thanks to the magic of skin effect, we can just add impedance to the coax. I got ahead of myself and covered that already. So then the path to the ground to the outside of the coax won't matter. The center conductor and the inside of the shield will have equal impedance to ground and will preserve our antenna pattern. Just what I wanted. So what we're going to do here, with the essence of a balun, really, is to go from balanced to unbalanced. We're going to have the outside of our coax, or both wires of our twin lead, floating. They're going to be separate from the ground. Nobody has a good sneak path to ground. No one has an unequal impedance to ground. And we're going to do that by either, well, really the easiest way by far is just to add a whole lot of impedance to the outside of the coax. Got some famous examples of that here. So some practical ways of blocking this common mode current. And again, I'm going to focus on coax because even if we're using twin lead, unless we're lucky enough to have a Johnson matchbox or a, something with a twin lead out, a balanced out, almost always that first step, the first few inches from our rig, our amp, our handy-talkie, are unbalanced. The coax shield is connected to the earth ground, the chassis of the amplifier, the chassis of the handy-talkie. So we have to deal with at least getting the first few feet of coax, or first few inches, balanced. We have to get it disconnected and floating above ground to get our feed line balanced. If you want to learn a lot more than what I'm going to cover, there are really only 2 references you need. This is a great slide to screenshot here. Kilo 9 Yankee Charlie.com, Jim Brown. He's been editing a series of books on fighting RFI in a lot of environments, home, warehouse, soundstage, wherever, for years, and updating them every year or so. And then, of course, the venerable ARRL antenna book, which used to talk about baluns on its own, but has actually licensed a great deal of the content that Jim Brown wrote. So if you have already bought the antenna book, check out chapter 24, and you'll find in printed or on your ebook reader a lot of the same comment that Jim Brown has. It is important to check a reference book or a recipe, as I might call it, when you're building a balun, because it's very easy to accidentally build something other than what you intended. There is a lot of great information about balun testing online. There's a lot of junk. This is the internet, but there's a lot of great information available online. Also, if you can find older versions of Jim Brown's RFI ham.pdf, he used to have a lot of different balun designs. He has kind of settled on his favorite and emphasizes that there used to be a wider selection of, let's take a lamp cord and make a kilowatt balun. He's backed away from a lot of that. There's still some of that in the ARRL antenna book, or again, if you can find an older copy. So at this point, surely this is the point we're going to expect me to talk about how important current baluns are and why voltage baluns are bad. Well, first off, my name's not Shirley, and the hospital, what is it? It's the building where all the doctors are, but that's not important right now. Any impedance transformer will have to change both the current and the voltage. If it's a 4-to-1 impedance transformer, you have to typically double the voltage and halve the current. That's the usual way we do that. The only real current-only baluns, what we usually mean, at least what I mean when I say that, is something that chokes off common mode imbalance I3, chokes off that unwanted current. It interrupts it. We add impedance to the outside of a cable. We're achieving balance. We're not transforming the impedance. We're floating our coax above the ground. We're cutting that connection on the outside of the shield. There was originally going to be a Dallas Amateur Radio Club lecture and lab where I talked about impedance transformers, because that's the topic I really can't have time to discuss here. Unfortunately, due to some scheduling and family issues, that has been pushed back indefinitely. But I will be sure to spread the word when probably next year when I get to give the impedance transformer presentation, I will share that news far and wide. We will also have a common parts kit you can order where we'll build, some good examples of a really high power 1-to-1 choke that works from 160 to 10 meters. We'll build a couple of impedance transformers out of inexpensive parts, and you'll kind of see how they work. So that's a commercial for something that hasn't even happened yet. A warning I wanted to add here is, the one thing I want to warn you away from. Impedance transformers do not perform predictably with reactive loads. I have that in red for a reason. There are some great examples online of people who built a 4-to-1 impedance transformer. They called it a 4-to-1 guanella balun, and they connected it to a severely mismatched load. I think it was a 43-foot vertical being used in all bands. And they found that the impedance transformations were nothing like what the label says. You don't get 4-to-1 when you have a lot of reactance. So my advice is if you're working into a random load, like a vertical for all bands, just use a really good 1-to-1 current balun to get your feed line isolated from ground, and then let your antenna matching unit, your antenna tuner, do the work of that impedance transformation. If you're working into a known impedance mismatch, like an end-fed half wave for a single band, go ahead and build the balun and the unun. It will make your life easier. It will do a good job. Your antenna is probably a single band, so you can even use an actual transformer, not a transmission line, and get a good match for that single band. If you have a known mismatch, go ahead and build an impedance transformer. If you have a random mismatch, just use a simple 1-to-1 current balun and let your matching unit sort it out. So I'm going to go over some common balun types here. The sleeve balun is another thing I'll warn you away from. We've all read about folding the braid back on our coax, right? It turns out that really doesn't work well and isn't necessary. I have done a lot of nets and had a lot of simplex talks on 2 meters just by pulling off the shield. You don't have to fold it back. That just adds a capacitor to your coax, which you generally don't need or want. A properly made sleeve balun is, just like I've marked here in red, shorted at the bottom, not the top, and it has to be spaced away from the coax by a significant amount, typically several coax diameters, in order to get that effect. Also, to really work well, you have to have it match the impedance of your coax. That is to say, if you're using a 50 ohm coax, you have to space your sleeve away from the shield in such a way as to also produce another 50 ohm coax. For practical amateur applications, this is not something most of us can build at home. When you see that on a website and they tell you to fold your braid, braid back, just skip that part. I've built this one. It works great. This is the famous, I remember even Radio Shack used to have this in their books, little circuit mini lab things, the Forrest Mims books. You use a coax to make, and this is unique, a 4-to-1 impedance transformer that is also a balun. It really does isolate your antenna from ground. Of course, it causes a lot of common mode current on your coax, but if you need your antenna to be balanced, then you don't worry about your feed line. This does it. It raises the impedance and it isolates your antenna from ground. The two warnings: it has a very narrow bandwidth, usually about 1%, and be careful of the velocity factor. If you snap the center conductor of one of your pieces of coax, I've done that, and then you have to peel a little bit more of the shield off, you'll end up on the wrong frequency, and the bandwidth is too small to cover you. So just be careful about that. This is another version of that, but it's very popular with amateurs who are feeding their beams, a single band beam antenna. This does not provide an impedance transformation. It does not cause the same maniacal common mode current problems as the other one. It just uses a quarter wave line versus a 3/4 wave line, so now one of them is half a wave out of phase, and gives you a balanced signal, again, isolated from ground at your antenna. Doesn't do anything about your feed line, but again, it gets your antenna isolated from ground and thus balances it. I've built a zillion of these. This is a bifilar transmission line of 100 ohms impedance. It's also known as lamp cord, or Ethernet for that matter. The vast majority of common wires, appliance repair wire, it turns out that if you separate them by the thickness of their insulation, are between 90 and 110 ohms. Who knew? Kind of neat. You get an instant 100 ohm feed line. Check online references for the number of turns to use. Use mix 31 ferrite. Mix 31 ferrites are amazing because they're the only ferrite mix designed to have a lot of loss. They don't make good impedance transformers because they waste your power, but they make wonderful common mode chokes because we want that power to be wasted. Balanced currents that are equal and opposite and isolated from ground cancel out. They produce no magnetic field in that toroid. None, because they're equal and opposite. An antenna current, a common mode current, will try to magnetize this lossy ferrite. It thus faces a high impedance, and any current that does flow mostly gets turned into heat. People have talked about melting their wire with these because they had a severe common mode problem, and then they introduced one of these and a lot of power, and the wire got really hot. But they work really well. They're easy to build. They cover a wide bandwidth. The parts are cheap. That's like I think over the past 10 years, the price of these has gone up. I think it's a $5 big toroid now. But it's cheaper than buying one, or cheaper than buying a finished Balun. Another variation on that is instead of making a lot of turns around a toroid, stack up a lot of beads. Instead of 10 turns around one inductor, have 10 inductors. Works the same way. They sometimes get hot, just like the other one does, but they have that same magical effect of cutting the coax shield on the outside and not the inside. Use plenty of beads. A usual goal is to get the job done in 10 or 12 inches because that's kind of affordable and not too heavy. If you need more length than that, it's usually best to pick a different ferrite. If you were using 43, switch to 73 or 31 or one of the many other types. If it gets too big and too heavy and too clunky. The other thing to be careful about these, they're very often exposed to the elements. Ferrite is brittle. If it bangs against things, they may chip. If it swings against the antenna support. You may want to enclose this in a piece of PVC pipe. Mix 31 ferrite is also available from online sellers in the form of a big clamp-on. This thing is like 2 inches and weighs about a pound. It's a hunk of iron and ceramic. This is practically a nuclear weapon for stamping out common mode current in things, any improvised thing. The cord from your generator or the feed line to a strange line antenna challenge fireplace. I used an old metal fireplace. It's a 20-meter vertical. I put 2 or 3 of these on my feed line and passed the feed line through it several times. I also have an inverter generator that emits vast quantities of noise on HF. So I like to put a couple of these on the cord and pass the cord through it a few times. It cuts that down a lot. An update, the first time I gave this presentation, Bill, I think it was N5BB, pointed out that at Tektronix, they had a lot of trouble with these. I think it was Bill. If the mating surfaces are not extremely clean, they lose significant amounts of effectiveness. So maybe not the highest precision device in the world. I've still had good luck with them. I wiped them off with a rag and I put my extension cords through them and they work great for silencing extension cords. So probably not adequate for laboratory work and measurement, but good for muffling your extension cords. I mentioned Jim Brown, I forget his call sign already, K9YC. I mentioned his rfiham.pdf and his Balun and Anand cookbook. He has, I've been up a few times there, a new preferred form for his Baluns. This will handle full legal limit, and it doesn't present an impedance bump. That little bit of a 100 ohm feed line makes a little impedance bump in your cable. He uses a premium type of RG58. It's called RG400. It's thin. It has a Teflon insulator inside it, so it can get very hot without harm. It can tolerate bending for long term without the center conductor migrating. So you can bend it in these very, very sharp bends, which you wouldn't want to do with like RG8 Mini or LMR400 or something. So he does this. He buys this RG400, which is $2 a foot, mind you. He puts connectors on each end, and he wraps it around a donut, one of these Type 31 toroids. You can make one of these that will cover almost every amateur band from 160 to 30 meters very well. And not 30 meters, excuse me, 30 megahertz, the top of 10 meters. And you get good performance. The coax is a little pricey, and it's a little stiff. You'll notice that this coax Balun has 4 zip ties on it. If you look carefully at the picture, you'll see 4 zip ties. Bending this stuff, if you have arthritis in your hands, hurts. If you don't have arthritis in your hands, it kind of hurts. So zip tie your cable down when you make these. The turns like to come undone. Once you make them, they're great. But that's my construction tip. They take a lot of power. Don't put it in the box. The coax is, it's just coax. Wrap the connections and weather seal those. Leave this out in the open air, and it will handle full legal limit. It'll get a little warm, but it's out in the open air. The heat will just dissipate. The ugly Balun is free. Please do beware, though. When you have a big coil of coax, you have a couple of challenges. First off, it has both inductance and capacitance. That makes it kind of sound like a LC circuit, kind of like a trap. And just like a trap, these ugly Baluns have peak impedance typically only on one narrow range of frequencies. And if this is a 6-meter antenna, let's say, or a 2-meter antenna, adding a whole lot of coax may add more loss than you want. Of course, if you only need 30 feet of feed line total, that may not matter. So do look online when you build these. Again, check references. A lot of people give rules of thumb, like take any coax you want and wrap 6 turns around it around a piece of pipe. That will give you some impedance on almost every band, but if you really have a strong urge to balance your feed line and separate it from the ground and cut down on antenna pattern distortion or RFI to the air conditioning like I did, this may not be appropriate for a multi-band antenna. It probably only is going to work really well on one. A technical note. There's a great site. Here's another link that you probably want to screenshot, where he hooked up his vector analyzer to a lot of these common, easy-to-build Baluns, and he tested them. The black bars mark places where the impedance was mostly resistive and not reactive. I'll explain why of that in a second. The color, red is weak, less than a kilo ohm. Green is great, more than 8,000 ohms. And you can see in this diagram that there are some simple chokes, like 8 turns of RG58 or that RG400 on one of those 2.4-inch Type 31 toroids. It's not the strongest impedance in the world. It's a couple thousand ohms, but it's mostly resistive from 80 meters up to the top of 10. So it's a great, if you're going to do summits on the air or operate portable from the park and you only want to take one Balun because they're heavy, hey, it's little, it's small, it covers a lot of bands. So make a note of this link, screenshot it. It's a great reference site where he tested a lot of these to see how they perform on different bands. The other thing that's worth noting is 160 is tough. It's low in frequency. It's hard to get enough impedance. And a Balun that you build for 160 is probably only going to really work well on 160. So if you need a lot of choking impedance, you're going to have a single band choke. So I think I either missed a slide here or I just forgot to say something. Oh yeah, I just forgot to read this text. A last note on construction. Baluns are not magical. They can solve that problem if you have common mode current on your feed line and you want to eliminate the pattern distortion or the interference that you're suffering from. Then making your antenna feed line float above the ground is a good solution. Isolating that antenna from the ground, isolating the coax from the ground will solve your problem. But there is no magic in radio, at least not with Baluns. If you accidentally added a whole bunch of inductive reactance to something that had a problem with capacitive reactance, suddenly you have just tuned the outside of your coax. There's much less impedance, and your common mode current will dramatically increase. So nothing is magic. Test, measure, read, look, experiment. You may not even need a balun, but I've hoped that I've covered why you might want one, the simple nature of what we really mean when we say balanced, floating above ground, equal impedance to ground for both conductors, and some quick tips give you an idea of what you might want to build. So I'm available here for questions. This is just a fun picture of one that shows a common 4-to-1 guanella balun with very unequal magnetic flux in its cores, which turns out to be normal. I'm available for questions if anyone has any. I'll try to answer, or you might know more than I do. Who knows?
Tony, you mentioned that some of those can get warm. When you say warm, is that just warm that you can still hold or whatever, or is it warm enough that you might have fire issues if you're not careful?
I have never heard of fire issues. I have heard of them getting hot enough when someone had a really severe common mode current problem and they were feeding a kilowatt into their antenna and they decided they were done with the common mode, so they put a long string of beads on the outside of their coax. I've heard of it getting hot enough to severely damage the coax, to melt the jacket off of it. So yeah, it's something you kind of have to test, and you may want to consider, making sure that your balun has good airflow to prevent it from overheating.
And the baluns are normally mounted outside anyway, so you've got airflow instead of up underneath your desk on the carpet, where it has very little airflow and plenty of things that can burn.
Yeah, and particularly if you build them out of coax, you can seal the coax connectors, and so you can leave the whole thing out there in the weather, for cooling.
Thank you.